Hello everyone. The purpose of this example is to demonstrate the use of SKUs, or stock keeping units, in SchedulePro. This video will show you how to define SKUs, how to associate multiple SKUs with the same production recipe, and how to schedule campaigns based on SKU order templates. Although the processes modeled in this example are yogurt production processes, the concepts explained in this video are not limited to these types of processes. They are applicable to any batch multi-product facility. Before viewing this video, please make sure you watch the Fundamentals of SchedulePro series of videos under the training page of our website. These 3 tutorial videos explain the basics of creating a project in SchedulePro, including information on how to create facilities and equipment, define recipes, assign resources, create campaigns, etc. Those concepts will not be repeated here. You may also view the SchedulePro overview video, which provides a summary of SchedulePro's capabilities. Furthermore, please note that the files that will be discussed during this video are part of the yogurt example that is shipped with SchedulePro. There is also a README file in PDF format associated with this example, which explains the example in greater detail. If you do not have a SchedulePro license, you may still download the README file from this link. You may also download the free evaluation version of SchedulePro from this link. The yogurt example discussed in this video can be opened and modified using the evaluation version or the full licensed version of SchedulePro. Additional information related to the creation and analysis of projects in SchedulePro is also available in the SchedulePro manual. Let's take a look at the yogurt production example now. In this tutorial, I will first describe a basic yogurt production process, as well as its associated equipment. I will then describe 5 cases which utilize this basic recipe. Case A represents the base case, where each product is described by a different recipe and no SKUs are defined yet. Case B shows how Case A can be simplified with the introduction of 3 different product SKUs that are all produced by the same recipe, with variances in certain processing conditions. Case C shows how to use bills of materials, or BOMs, to define which raw materials and intermediates are required to produce a given product SKU. These BOMs can then be linked to recipe streams to account for consumption of the materials. This case also describes how to specify variable operation durations based on SKU types, such as product type, product size, etc. Case D describes the storage and use of intermediate SKUs. This is beneficial in cases where a certain intermediate is used in the production of multiple final products. Scheduling considerations related to this type of scenario are also discussed. The final case covers SKU order-based scheduling. This provides a semi-automated way to determine which intermediate and final product campaigns should be scheduled and when they should be scheduled, based upon the final product SKUs that must be prepared in order to fulfill the order. An order may represent either an external customer order or an internal production plan. This will conclude this example. There are 3 videos associated with this example. The first video describes the basic yogurt production process and covers cases A and B. The second video covers case C, and the third video covers cases D and E. I will describe the basic example process now. In this example, stirred yogurt is being produced within a plant in a variety of fruit flavors, and packed in a variety of container sizes. In all cases, the production recipe involves a sequence of common steps shown in this diagram. At the beginning of this process, pasteurized milk is sent to a sterilized fermentation tank. Next, starter culture is added and heat is applied in order to ferment the mixture into yogurt. The yogurt is then transferred through a cooler to a storage tank, and finally it is sent to a filling line for packaging. An inline mixer in the transfer to filler line may optionally add a fruit flavor in puree or syrup form to the yogurt. This yogurt plant has 3 identical 12 metric ton tanks for fermentation and another 3 tanks for storage. Yogurt is filled in 3 different container sizes: 200 gram, 500 gram, and 1 kilogram. Filler throughput is dependent on the container size, with the processing rate decreasing for smaller cup sizes. Switching to the SchedulePro interface, we can see the recipes that have been defined for the Case A example. To represent the production of plain yogurt in the 3 different cup sizes, 3 different recipes were developed. These recipes are identical except for the filling rate. We can visualize a recipe in the form of a Gantt chart by selecting the recipe and clicking this button. The procedures within this recipe are displayed with dark blue bars. The operations within each of these procedures are represented by the light blue bars. The specifications for a given operation can be viewed and edited by right-clicking that operation and choosing Operation Data. Switching to the Duration tab, we can see that the duration of this operation has been specified as rate-based. Here you can see that the 12 metric ton batch will be processed at a rate of 3 metric tons per hour. This rate has been determined based on the minimum rate specified for the associated main equipment item, in this case filler FL101. Based on these specifications, the filling operation in the 200 gram recipe takes 4 hours. The filling operations for the other 2 recipes take less than 4 hours because they are based on the nominal and maximum rates assigned to the filler. These minimum, nominal, and maximum rates for the filler were specified within the Yogurt Facilities Equipment database on the Size tab of filler FL101's Equipment Properties dialog. Note that several cleaning, or CIP, operations have been included in this production recipe. These operations will take place during every batch of yogurt production. Cleaning activities may also be scheduled to occur at the beginning or end of an entire campaign. This is done from the Advanced tab of the Campaign Properties dialog. In this case, the post-campaign cleaning duration for filler FL101 will be based on the cleanout time specified on the Cleanout Changeover tab of filler FL101's Equipment Properties dialog. This is specified within the yogurt plant's equipment database. After the recipes have been defined, production campaigns can be scheduled. The plant schedule can then be viewed by clicking the Equipment Occupancy Chart, or EOC, button. This chart shows the equipment occupancy chart for a production sequence comprising 8 batches of each of the 3 products: yogurt in 200 gram, 500 gram, or 1 kilogram cups, represented by the yellow, red, and blue bars respectively. As you can see in this EOC, when a batch of 200 gram containers is executed, the filler rate is low, and the filling step in FL101 is the process bottleneck. In contrast, for batches of larger container sizes, there is idle time between batches in the filler, and the fermenters become the bottleneck. Also notice that post-campaign cleaning activities, shown in white bars, are included after each campaign in filler FL101. The cleaning activities associated with the fermentation and storage procedures in every batch are also shown in white, regardless of which campaign they are associated with. This was accomplished by specifying that cleaning operations within each recipe should be assigned to the CIP operation type, and the default style option for the EOC should be overridden. For information on how to do this, please refer to the README file for this example. In case A, the representation of 3 different products required the declaration of 3 separate recipes, which are essentially identical except for the filling rate specifications. The development of SKU functionality in SchedulePro was motivated partly by the desire to unify the representation of the production of similar products while allowing the explicit declaration of their processing differences. An SKU is a code representing a raw material, intermediate, or final product that is ordered or produced and stored in the facility. Different SKUs may refer to the same product with differences in the packaging size, labeling, etc. This next case, case B, shows how to incorporate SKU concepts into SchedulePro. Although SKUs are in essence materials, in SchedulePro they are listed under a different heading to emphasize the special role they play in a company setting. However, materials and SKUs are not entirely foreign entities, since SKUs may be composed of materials. Furthermore, different SKUs may utilize the same raw materials or intermediates. Therefore, by tracking SKUs, their common materials can also be tracked. SKUs are declared in the pane that is displayed when the SKUs branch is selected from the Explorer tree. As you can see, 2 final product SKUs have already been created in this file. To declare a new SKU, first click this button. In this dialog, it is necessary to declare a unique SKU codename, the SKU type, and the amount reference basis. All the SKUs in this file have been declared as discrete, since their quantities are measured by the number of yogurt cups produced, and all of them were designated as product type SKUs. For an intermediate or product SKU, its definition also optionally involves the declaration of its bill of materials, or BOM. This is simply the list of raw materials and/or input SKUs and their corresponding amounts required for the new SKU's production. The detailed discussion on BOMs will be deferred to the Case C scenario. If desired, you may also add an explanatory description text, the composition, material, and storage unit, the SKU's purchase cost or selling price, depending on its type, and a specific display color for batches in the EOC representing the production of that SKU. The new SKU shown here, and the 2 previously created SKUs, represent stirred yogurt packaged in the 3 different container sizes used in Case A. As mentioned previously, an SKU can be linked to a storage unit through the SKU Properties dialog if that storage unit already exists. If the storage unit does not yet exist, a new one can be created by navigating to the Storage node in the Explorer tree and clicking the Add New Storage Unit button. In the New Storage Unit dialog that comes up, a unique name should be chosen for the unit. Then, the new storage unit can be associated with the raw material SKU that was created a few minutes ago. The association of the new storage unit with an SKU forces the new storage unit's specifications to conform to those of the SKU. Since the SKU associated with this unit was specified as a product quantified as discrete entities, the storage unit was also automatically classified as a product unit whose contents are measured as discrete items. The association of a storage unit with a specific SKU implies that all drawings or deposits associated with that SKU will come from or go to that unit. Note that if it is important to track the inventory of this unit, the Track Inventory box on the Inventory Data tab should be checked on. A capacity of 200,000 entities will be specified for this particular unit. After creating the relevant SKUs, we must assign them to specific recipes. This step is required because the definition of an intermediate or product SKU is independent of the declaration of the recipe that produces it. However, the two need to be matched so that SchedulePro knows which recipe to execute when a particular SKU is to be produced. Unlike case A, in case B, we only need to declare a single recipe, shown here. This recipe will be shared by all three product SKUs. Recipe sharing does not necessarily mean that there are no processing differences when the common recipe is used to produce any of the SKUs. In fact, SchedulePro allows shared recipe differentiation based on equipment processing rates as well as changeover and cleaning times. A few of these differences are SKU-based, while many are SKU type-based. For the latter, it is necessary to declare the different types that SKUs may belong to under the Options Recipe SKU Types menu. For more information on this, please refer to the README file for this example. The definition of SKU types allows the differentiation of some processing conditions based on those types. In this case, we wish to base the filler's processing rate on the container size. To do this, we must return to the Size tab for filler FL101. Notice that whereas the original rate specifications in case A were simply based on the nominal, maximum, and minimum capacities, now the filling rates for each type of SKU are based on the packing size. This allows many additional rates to be defined for various product types, if desired. Also notice that rates can be differentiated based either on individual SKUs or based on SKU type classifications. In the former case, users should add each of the SKUs for which a different rate applies, otherwise the nominal rate is used. In the latter case, the table is filled with all the types declared for the selected category, and the user enters the rate values. An empty rate value for a type would mean that the nominal equipment rate should be used for that type. Notice that rate values have already been entered for all three of our packing sizes in this example. Now we are in a position to match the SKUs to the common production recipe named stirred yogurt. To do this, we must return to the SKU node of the Explorer tree. In this example, the first two SKUs have already been associated with the recipe, and now we must assign the third SKU to the same recipe. This can be done by selecting the final SKU and clicking on the Assign SKU Production Recipe button. Next, the Associate SKU Production with Recipe box must be checked, and the single stirred yogurt recipe must be selected. This signifies that the 1 kilogram SKU is produced using the stirred yogurt recipe. To complete the association, the operation in the recipe that produces the SKU must be declared. Therefore, I will select the Fill procedure and the Filling operation in the corresponding drop-down menus. The specification of this producing operation is important in order to properly time the generation of the final product. Next, in the Nominal Amount box, the stream responsible for the production of the SKU is specified. There are two options here. Either an existing recipe stream in the specified operation is used, or a new stream independent of the recipe is created. In the former case, the SKU produced amount is set equal to the amount declared in the recipe stream. Note that the stream type and material basis should match that of the SKU for the association to be possible. In the latter case, a new recipe-independent stream is created with a material basis and amount specified by the user. This does not affect the original recipe. For this example, I will specify a new stream independent of the recipe to produce a nominal batch size of 12,000 entities, where each entity is a 1 kilogram cup. This corresponds exactly to the nominal amount defined for the stirred yogurt recipe batch size, which is 12 metric tons, and therefore the value of the corresponding recipe scale factor in the dialog is set to 1. The specification of the corresponding recipe scale factor is very important because it is used to scale all other amounts, operation durations, etc. in the recipe when this recipe is used to generate batches for this SKU. Finally, in the bottom half of this dialog, the SKU types that will be considered when scheduling the selected recipe are defined. There are two options here. Either the recipe types declared within the recipe are used, or these types are overwritten for the SKU. In this case, I want to overwrite the recipe types and declare the 1 kilogram classification as the packing size type of this SKU. This specification will force the recipe to use any type-specific data specified, in this case the type-specific filler rate, when it schedules a batch of 1 kilogram SKU. With the introduction of SKUs, campaign definition can be done either based on recipes or on SKUs that have been matched with a recipe. To do this, select the Production Schedule node of the Explorer tree and click the Add New Campaign button. Notice that you have the option to either generate a campaign associated with a recipe or generate a campaign with an SKU. To create a new SKU-based campaign, select this option, and then select a particular SKU. Notice that the recipe list box at the top is no longer modifiable, and the recipe that has been matched to the selected SKU is shown. The campaign color is also automatically set to the color associated with the selected SKU. Next, I will specify that this campaign contains 8 batches. Note that the amount of product associated with a certain number of batches can be updated by clicking the Recalculate button here. Also note that when the campaign definition is SKU-based, the nominal amount in the SKU recipe matching dialog presented earlier is considered the nominal batch size. In this case, the nominal production amount for 1 kilogram SKU was set to 12,000 entities, so 8 batches would produce 96,000 1 kilogram containers. Continuing on to the Time Sequencing tab, I will make sure the campaign start time is scheduled appropriately. In this case, I want the campaign to begin on or after the default release date of January 20th, 2014. As shown here. Next, I will visit the Advanced tab in order to specify that cleaning should occur after the filler is used for the final time in this campaign. To do this, I must click the Cleaning checkbox under the Post-Production options. Now the Setup button can be clicked, and the Equipment Setup Cleanout Time option can be chosen as the basis for the cleaning duration. With these specifications, the filler will be required to undergo a 1-hour cleaning after it is used in the final batch of this campaign. This cleaning duration is based upon the equipment cleaning requirements that were specified when filler FL101 was defined in the equipment database. Now I will schedule all the campaigns and open the EOC. The chart shown here is identical to the chart produced for Case A. The only difference is that in this representation we have used a single recipe, and we have introduced the production variances through SKUs linked with this common recipe. This is possible because at scheduling time, the recipe is transformed to serve the specific needs of each SKU which is produced through that recipe. In this case, this transformation involved the use of SKU-specific filling rates and the addition of SKU-producing streams that did not exist in the original recipe. The stream results can be visualized by generating the inventory chart of the 1 kilogram storage unit. Here, the production of the corresponding 1 kilogram SKU is clearly shown, even though there was no output stream to the 1 kilogram storage unit defined in the original recipe. This concludes part 1 of this video series.